All right, welcome class to lecture 9. In the last couple lectures, we've really finalized what are the most important results for working with statistical mechanics in practice. We've elaborated on a concept finally of statistical ensembles, which really lay the basic framework for the application of statistical mechanics to systems of interest. So really, we are in a position now where all the basic formalism for equilibrium statistical mechanics is on the table, and we are in a position to pick up that formalism and start applying it. So we're going to start building towards, in the next few weeks of this of lectures, less formalism and more tricks to practically evaluate things like partition functions and study likelihoods, compute quantities that are then macroscopically observable. So this really derives from a notion that we've finally introduced and began elaborating on of statistical ensembles. The definition of a set of constraints on a system, physical constraints like fixed energy, and the impact that those constraints have on probabilistic statements of the corresponding microstates that that system can then sample. So the ensemble is really a way of defining which states we can see under a set of constraints. And we now have the tools and have derived in various specific instances what our fundamental postulate has to say about those likelihoods. So I want to kind of recap a little bit the ensembles we've bumped into thus far, some of the structures that we've noticed in this kind of first 10 minutes or so of class. And then really the rest of this lecture and the rest of a number of lectures for the next couple of weeks are taking these results and beginning to apply them. So the statistical ensembles we've bumped into so far really began with our fundamental postulate. We didn't call it the microcanonical ensemble to begin with, but that's really where we started. That microcanonical ensemble just refers to the distribution of microstates for a system that is stuffed into a box where the energy, volume, and number of particles are held fixed. So this is our rigid, impermeable, and insulated box where those conserved quantities are conserved. And consequently, we had, through our postulate, an assignment of probability for a microstate in such a system. In this case, just all microstates are equally likely. So they are all equal to some constant independent of that microstate. But with the constraint that that microstate satisfied those fixed quantities of E, V, and N. Through the Boltzmann definition, we gained access from that probabilistic statement to a statement of thermodynamics, namely that the entropy, having units of KB, was equal to the log of omega. Now, log entering in, again, because typically the numbers of microstates grow exponentially in the scale of the system. So if I take a log, I have something that grows linearly. And thus the entropy being an extensive quantity, this is then a sensible definition for it. Now, in a ensemble where the energy, volume, and number of particles are fixed, that necessarily means that conjugate variables to those three fluctuate. So we would see fluctuations, for example, in the temperature, pressure, and chemical potential. Those are then not fixed quantities, but measurable quantities through, for example, enumerating how the number of states changes as I change the energy of that system. For example, for the temperature. From that microcanonical ensemble, we learned what happens if instead of fixing the energy, we open the system up a little bit and allow for the energy to be exchanged with a bath at a fixed temperature. This generates a different ensemble, different set of microstates with different associated probabilities, and we call this set of states the canonical ensemble. In such an ensemble, the energy is not fixed, but the temperature is, but we remain rigid and impermeable, so the volume and number of particles are fixed. As we've seen explicitly, that means that the energy is now a fluctuating quantity. It has a mean and a variance and all other higher order moments or cumulants. Analogously, the pressure and chemical potential would be fluctuating statistical quantities in such an ensemble. When we fix the temperature, we noted that this endows a system with a bias. States are no longer equally likely, but rather exponentially likely depending on their energy. A system with higher energy is exponentially less likely than a system with low energy, with a strength of the bias that is exactly that temperature in units of kb, often written for simplicity as beta. Normalizing this distribution introduces another partition function, another normalization constant. In this case, we've called Q. And just as in Boltzmann's definition, we find that if we take the log of Q, put it in units of kBt, and add a minus sign to be consistent with typical definitions, we find that that partition function encodes a relationship between microscopics and thermodynamics, in this case through the Helmholtz free energy. I can write that a little more cleanly. Helmholtz free energy A is minus kBt log Q. All right, now finally, last lecture, we opened up the system a little bit further, defining the so-called grand canonical ensemble, whereby not only was the temperature and volume fixed, but in this case we fixed the chemical potential of a surrounding bath, therefore dictating that energy, pressure, and the number of particles in the system fluctuate. Now, we derived this the implication for opening the system up to exchange of particles on the probability of a microstate, but it has a structure that you now might be able to anticipate, whereby in the canonical ensemble, by allowing energy to fluctuate, we find an exponential bias on the microstate probability on that energy. Here in the grand canonical ensemble, it is open to changes in energy, so that bias is still there. But in addition, we find that the probabilities are now exponentially suppressed in a factor of beta mu times the number of particles in that system. We introduce that capital C as a partition function in this case, and again, taking the log of this number, we find a relationship to thermodynamics. In this case, a slightly awkward one, mind you, that the log of this grand canonical partition function is equal to beta PV. So these are very common sets of constraints, fixing the energy or the temperature and the chemical potential. By no means enumerate all of the possible ways one can fix the system. You'll have slightly more experience understanding, a different case where you fix the pressure instead of the volume, forming the so-called isobaric ensemble. I don't want you to get bogged down in these names. These names are useful only to the extent that they provide a shorthand. So instead of saying, I'm going to fix the energy, volume, and number of particles, I can just say microcanonical ensemble. What shouldn't be lost, however, are that these are all just referring to different sorts of constraints, and all of those constraints have derivable consequences on the statistics of a system. In enumerating these ensembles, however, we find a very common structure. This exponential suppression probabilities and these relationships between normalization constants and thermodynamic properties. So a very important conceptual object that gets introduced are indeed these different partition functions, omega, Q, and capital C. Each of which encode a lot of useful information. So we call them partition functions because they quantify the likelihood of groups or partitions of states. So the relative likelihood of seeing a group of states B relative to a group of states C is equal to a ratio of the partition functions where the sums are carried over those states in B or C. Through these thermodynamic relationships, like the fact that the Helmholtz free energy is the log of Q, or the pressure is the log of C, or the entropy is the log of omega, we find that ratios of partition functions are then also equal to exponentials of changes in thermodynamic quantities. For example, in this case, in the canonical ensemble, a ratio of partition functions is an exponential difference in Helmholtz free energies, which is also equal to a ratio of probabilities. Now, we introduced the Helmholtz free energy back in the day because it is a measure of work. So another way to write all of this would be noting that the change in the Helmholtz free energy is just the reversible work for some process. In this case, it's the reversible work to take a group of C states and transform them into the group B states. So now we have really a sequence of relationships that really go from basic statistical statements, relative likelihoods, all the way to mechanical quantities, the work required to perform a transformation. So indeed, calculating or approximating or manipulating partition functions will give us tremendous amount of information on systems we care about. If we can enumerate them, we'll, for example, find relative likelihoods, but even if we just look at things like their derivatives, how they change with variables, we get a lot of information there too. For example, partition functions are also cumulant generating functions, which is a very fancy way of saying that if I take the derivative of log Q with respect to minus beta, I will, for example, get the average energy. If I take two derivatives, I'll get the second cumulant, so-called variance, which is also the derivative with respect to beta of the average energy, which through the chain rule gives us kBT squared, how the energy changes with temperature, which is what we call the heat capacity. All right, so that's kind of where we've been. That's an elaboration on the sort of structure we uncover through these different ensembles and their associated partition functions. Today really is an example of how you go ahead and work to compute those partition functions in different contexts. So I want to start by revisiting that lattice gas calculation we did last lecture, working with the grand canonical ensemble. And then I want to move to more realistic settings like how we ended the last lecture, where we posed the question of what on earth are we meant to do if we have a system that lives in a continuum and we need to count its states. Okay, so let's go back first to working with the grand canonical ensemble, GCE, and consider a lattice gas again. And in that lattice, by gas, what I really mean is that these are a set of non-interacting solutes distributed within this lattice. So let's have fun. Let's imagine gridding up space. This is a little piece of my beaker. These squiggly lines will denote the fact that particles can come in and out of this space. You can imagine filling it with solutes, these little blobs. In some of those lattices, an instantaneous configuration, for example, might not have a solute in it. So imagine that this is lattice site I. If it has no solute, the variable ni will return 0. If it has a solute, say in lattice site J, n will return 1. So I have then a binary variable that tells me whether each one of my sites is filled or empty. If these are non-interacting and dilute, I can ignore the likelihood that there are more than one solutes in any given site. If they're non-interacting, that's essentially a way of saying that the energy just depends on the number of, does not depend on the arrangements of the solute. So if all I'm considering in this calculation is different arrangements of solutes, I'm free to set the energy to be whatever constant I want. It'll be convenient to just set it to 0. The number of solutes in the system at any given time is something that is computable just by summing over all the lattice sites. Let's say that they go from 1 to m. If I have m cells, and if I just count up those binary variables, that will return then the overall number of solutes in the system. Now to compute the partition function in this grand canonical ensemble, we'll need to sum over microstates, as we always do to compute any partition function. Which means that we need to be able to know what defines that microstate. So in this case, a microstate, an instantaneous state of the system, is defined by a sequence of those binary variables in 1 to nm, which tells me whether or not each one of those sites is filled or empty. Then I can proceed fairly straightforwardly. This partition function is a sum over microstates weighted by the energy of that state, and beta mu the number of particles in that state. I have set the energy of all states to be the same and just 0, so that term will go away. This term here is just a sum over ni. So now I can anticipate that the structure of this calculation is going to be tractable. Pulling out this sum, what that really means is summing over all the microstates means that I need to sum over all the different states that N1 could be. which are 0 and 1, all the different states n2 could be, all the way up to all the different states m, n, m can be, weighted by e to the beta mu, that's sum over ni, which is a representation for the number of particles in the system. And this, because it is an exponential of a sum, factorizes into a product of exponentials, each of which I can attribute to its own sum. So again, the linearity of this problem, the fact that I can express n as a sum of independent variables, of the independent fluctuating quantities, little n's, means that this whole problem factorizes and reduces down to a problem of only computing a single cell partition function. So I'll get m factors of one of those sums weighted by its own Boltzmann factor. Due to this factorization of the Boltzmann factor. So this is something easy to do. I get m factors of 1 plus e to the beta mu. The 1 coming from when I put in n, little n is 0, the e to the beta mu, where little n is 1. This is e to the beta mu is kind of an obnoxious quantity to keep writing, so I'm just going to define this as z. This turns out to be what many people would call the activity of a solution. And now, once I've computed the partition function, I have access to all sorts of statistical quantities that describe that system. For example, I can compute the average number of particles by taking the derivative of that partition function with respect to beta mu, holding temperature and volume fixed. And that's an easy derivative to take. Log of 1 plus z to the m, well, that brings down in m. If I take a derivative with respect to beta mu, that gives me an exponential on top, which is z, and 1 plus z on bottom. Now, z doesn't mean a lot to me. It's hard to kind of intuit what that actually is telling you about the average number of particles. It behooves us then to try to manipulate this into a form which makes more sense. So if I define f as the fraction of occupied cells, well, that is, through the calculation we've just done, equal to z over 1 plus z, which can be solved for z. Inverted, that gives me f over 1 minus f, or that z plus 1 is equal to 1 over 1 minus f by adding 1 to both sides. Those are just different representations that then will relate the average number of particles, just rewriting the average number of particles in terms of that fraction. We have then that, 1 over 1 minus the average number of particles is that activity plus 1. That doesn't look like it's so useful, but since beta PV is equal to log of that partition function, we have, through these relationships, a way of rewriting the partition function as 1 plus z, that is then log of 1 over 1 minus f, which if F is small, is nothing but, times M, sorry, is nothing but M times F. So we have a relationship between the pressure and the fraction of occupied cells, which all the cool kids know is just a way of saying that beta PV is equal to average N, or PV is equal to KBT in the macroscopic limit. So maybe it's worth stepping through this again a little bit clearly. So log of 1 minus x is minus x. And we've just flipped that upside down. Okay. All right, so we've done that already. Hopefully it's sinking in, doing it over again. Again, the linearity of this problem, the non-interacting aspect of this problem makes the calculation tractable. Okay, so what about more realistic gases? How do we think about them? We kind of bumped into an awkwardness when we started this discussion last lecture. So let's consider a system in the canonical ensemble where I fix T, V, and N. And let's start by considering a single particle in a one-dimensional box. So it's an easy system to draw. Here's my one-dimensional box. This is the x direction. That box has length L. And I have one little particle. Let's color it blue. That can move within that box. So if I wanted to think about the mechanics of that particle, for example, assigning an energy, how would I do that? I have a single particle in a box. What's its energy? Well, if we're really true to ourselves, we would know that it kind of depends. It depends on whether or not we're trying to consider that particle as a quantum particle, in which case the energy is given by a set of eigenvalues, the solutions to the Schrodinger equation for this system with hard walls. Or if it's a classical particle, it'll have an energy function that is a continuum given, for example, just by its kinetic energy. So we're going to consider it both ways and essentially convince you that it doesn't really matter. That's the kind of goal. Okay, so let's start classically first. Let's denote that Cm for classical mechanics, in which case it is perfectly fine to define the state of the system by knowing where that particle is and how fast it's going. Quantum mechanically, this is something that's not allowed, but classically it's perfectly fine. So if I think about this as being a billiard ball rather than an electron, the energy 1/2 mx squared is just the kinetic energy, where that v is just a number, not an operator. And we have some boundary conditions that says that the x is, the potential is 0 so long as the particle is in that box. So I have my microstate, I have my energy. In principle, it seems like I have all the information in order to try to go through and compute the partition function. So you know you need to sum over microstates, which in this case means summing over all the possible x's, possible vx's, weighted by this Boltzmann factor. But here's the awkwardness, as alluded to last time. How do we count? Whoop. How do we count x or vx? How many ways can I put that particle down on the line? A reasonable answer to that is infinity. There's an infinite number of numbers between 0 and L. Those pragmatic students listening to this might say, well, does it really matter if a particle is at 0.99999 L? Is that significantly different from 0.999 L? Is that a different state? Can I meaningfully distinguish that? It, I think, is intuitive that there is some resolution below which, for practicalities, the states are not really all that different. Now, that should strike others of you as a somewhat uncomfortable thing to do because it does seem arbitrary. So let's actually proceed in this kind of arbitrary way by introducing a scale, a resolution below which we'll just say we'll group all states together, and we'll see if it matters. We'll see that if we go through that calculation that computable quantities depend on that scale or not. If they do, we have a problem because an arbitrary choice is affecting our answer. If computable quantities are independent, well, maybe it doesn't really matter what that scale is. Okay, but let's start by introducing a scale. So I have Vx in one direction, x in another, and now rather than being a continuum, let's imagine that I grid up x and Vx. So that a particle with this value of x and Vx is one configuration, one microstate. To do this, I need to define how big those bins in x are and how big they are in Vx. Let's call that delta x and delta Vx. All right, so if that is the case, that in the limit that delta x and delta Vx go to 0, a sum over those infinitesimal area elements becomes an integral. So I integrate over x and I integrate over Vx. Right? Now, look at that for a moment. Up here, we have Q is a sum of those exponentials. What are the units of Q there? What's unitless? Q is just a number. It's the number of thermally accessible microstates. What about the units here? Taking those sums to integrals, now looks like we have units of action, length times velocity. So indeed, that can't be quite right. If we did this carefully, we'd find that we need to introduce those scales here to take that limit. Otherwise, we would just end up with infinity again. Okay, so now we have a representation, a couple integrals that we just need to do to compute this partition function. We need to decide the limits. So what are the possible values x can take? Well, that's 0 to L. What are the possible values Vx can take? Well, in principle, it could be anything from -infinity to infinity. That too is a little awkward. For those of you who know anything about relativity, if a particle is infinitely fast, that doesn't seem like a very good thing for it to do. Einstein would have something to say about it, but we're going to neglect that. Essentially because when we put in the form of this probability, m over 2 Vx squared, the probability that a particle has an infinite velocity is essentially 0. So whether or not it is really infinite or just very, very large, it doesn't really matter. So we can neglect effects from relativity, at least for particles that have reasonable masses. If these were photons, maybe things will be a little different. All right, so this first integral is easy to do. That just gives us L. The second integral is a little more complicated. If we have a little aside here, it's an integral of the form -infinity to infinity e to the -ay squared. That is a so-called Gaussian integral. It has the value of the square root of pi over a. This is an integral we will see a lot of, so it will behoove you to remember it. And I will never, the exams will be, open book, so it doesn't really matter if you memorize it, but you'll certainly have an easier time with the rest of your life if you just commit this to memory. Okay, so that's a Gaussian integral we can do. Playing the role of y is Vx, playing the role of a, therefore, is beta m by 2. So we will get a factor of pi, as they tell us to, 2 up top and beta m down below. Good, so we have computed the partition function for this classical particle and found that it is proportional to things like L and beta to the -1/2. That proportionality is useful to note because, for example, if we were to compute the derivative of log of q with respect to minus beta, we know we'll get the average energy if we do that. Log of q, if I have a product of terms, when I take the log, I get a sum. So I have d beta, log of q gives me log of beta to the -1/2, plus log of L, plus a constant. When I take the derivative, it doesn't matter what that constant is, it'll go away. The derivative with respect to beta of log beta to the -1/2 gives me -1/2 over beta, which is what I like to call 1/2 kBt. And so the average energy of this particle moving in this box is just a function of the temperature. It does not, for example, depend on the mass. Now, the mass is the only thing that tells you that this particle is a neon atom, for example, or a nitrogen, a hydrogen atom, or a helium atom. M is the only thing that tells you what the identity of that particle is. So this is actually a pretty peculiar result. It tells you that all particles have average kinetic energies in one dimensions of 1/2 kBt, independent of what the particle is. So a classical particle, having just kinetic energy, has identically the same kinetic energy, independent of what it is. So I can have heavy water or light water. If I put an individual water molecule in the gas phase, it's center of mass translational motion will be associated with a function just of the temperature. All right, so that's nice also because those constants, the dx and delta vx, don't enter into this expression. So we had to introduce this artificial scale, and while the partition function, the number of thermally accessible states, are certainly counted in those units, when we compute things like the average energy, or if we computed the heat capacity, take another derivative, we wouldn't find a function of that scale. So in some sense, it seems like we've lucked out a bit. We've introduced an arbitrary scale, but our answer doesn't depend on it. But we should check our work. We should make sure that this actually does make sense. And we can do that by proceeding quantum mechanically. What I'll denote as QM. Now, quantum mechanically, for this particle in the box, I can no longer tell you that it has a position and a velocity. The way I represent the system is very different. In fact, the way that I could represent the system is essentially by telling you what eigenstate it's in. For example, if I was to look at some energy levels, either it is in some ground state, or it is in some excited state, or some higher excited state. So now the microstate of the system is really given by one number. It is what eigenstate the system is in. And I can attribute an energy to that microstate by knowing how the energy levels of a particle in a box are distributed. I happen to know that these go like that microstate squared, or that eigenstate number, quantum number squared, with factors out in front that depend on things like Planck's constant, the mass of the particle, and the length of the box. So these are the eigenstates or eigenenergies one more time, eigenenergies for a particle in a box. All right. Well, just as before, if I didn't tell you anything about the system, I've just we have elaborated on how to count microstates, what they're described by, and their associated energies. So there's nothing precluding us then from just continuing on and trying to compute the partition function. I need to sum over the microstates, so in this case, just summing over n. N happens to run from 0 to infinity. I need to sum those Boltzmann factors, which in this case are e to the minus beta, h squared, 8ml squared, n squared. So if I can compute that sum, I can therefore have computed the partition function. Now there's a bit of a bummer. I don't know how to do that sum. I could approximate it in a couple different ways. For example, if L is macroscopic, so I'm imagining that this particle lives in a macroscopic box, like a gas particle in the room I'm sitting in, then L is a number that is on a length scale of meters. H and M are all numbers that are microscopic, which means that if I do the unit conversion, if I put something that is on the scale of meters in that denominator, I'll find that it is much, much less than kBt. So that at different n's, as I go from n is 1 to n is 2, this number, beta times h squared over 8ml squared, varies very, very slowly. In fact, so slowly that this sum, that essentially the spacing between the energy levels, looks like a continuum, which means that I can approximate that sum as an integral. Now I'm counting, I'm discretizing an n, which then gives me a delta n, which has unitless, n is equal to 1. So I have no prefactor in this case. If those energy levels vary so smoothly, it doesn't really matter if I start from 1 and go to infinity or go from 0 to infinity, I'll get the same answer. And now that is an integral, which is exactly the same form as the integral we just did. It's a Gaussian integral, which means I can compute it. In this case, it's half of a Gaussian integral, and playing the role of A is beta h squared. I get a 2, I get an 8 pi m l squared. And that's all to the 1/2. Now note, let's see what we've just found. We found that Q is proportional to the square root of L squared, that's just L, and beta to the -1/2. That's the same functional dependence that we found in the classical system, which means immediately that if we took the derivative to compute the average energy, we would analogously get 1/2 kBt. Which is pretty neat. It's the same answer. So proceeding quantum mechanically or classically, at least in this specific limit, we get the same answer. So why is that? Why aren't they different? That's a reasonable question to ask. Well, if this assumption is true, so h squared over 8ml squared is much, much less than kBt, what really makes quantum mechanics unique is that I have discrete states that I live in, rather than the kinetic energy being any of a continuum number, because V is anything between -infinity to infinity. N is an integer. And so I have integer values of the kinetic energy that I could actually observe. But if this is true, if I actually plotted those energy levels, what I would see is a continuum. On the scale of kBt. So the discreteness in this limit of a macroscopic box is irrelevant. At least for a macroscopic box, and I have to tell you the temperature at things like ambient temperatures. Now, of course, this would break down if I went to very small boxes or very low temperatures. I'd start to notice that discreteness, in which case this approximation to turn the sum into an integral wouldn't hold, and I would in general get a different result. But in the right limits, so thinking about a particle in a macroscopic box at ambient conditions, quantum and classical mechanics agree. So in fact, if we work on those scales under those conditions, we're essentially free for free particles to choose whatever way of doing the calculation is convenient. And more than that, the equivalency or the agreement between these two results gives us some insight as to how we should have set the scale that we counted up states in, because note, we didn't introduce a scale, didn't have to introduce a scale in this calculation. So what does this mean? So if we took the classical mechanics result, which was L in units of delta x and 2 pi beta m square root of in units of delta Vx, and compared it to the quantum mechanical result of Lm over h square root of 2 pi beta m, those things look pretty similar. So I've just simplified this result, noting that the square root of h squared is just h. That if I bring 1/2 times the square root of 8, that just gives me a 2 under the square root. So they look pretty similar. So if these are free to choose, if I chose delta x, delta Vx to be, what do I need to choose it to be? So the 2 pi over beta m is the same, L's are the same. I need delta x, delta Vx to be h over m. Then the classical mechanics result would be the quantum mechanics result. If I bring the m over to the other side, I have delta x, m times v, well, that's a momentum. Hey, look at that. What is that? Delta x, delta p is h. You all probably bumped into that before. That's Heisenberg's uncertainty principle. He told us essentially what the right scale is, that it doesn't make sense to assign unique microstates on scales that are less than that associated with Planck's constant. Everything within a box delta x by delta p equaling h is essentially indistinguishable at a really fundamental level. They really are the same microstate. All right. You guys still watch Breaking Bad? Is that still a thing for you kiddos? All right, anyway, so let's move on. So we've just arrived at a way of thinking about free particle motion in boxes in one dimension. We can go a little bit further. We can generalize the classic or the quantum, let's do the classical mechanics results to 3D. Here, the microstate of the system, I have to give you more numbers. I have to tell you where the particle is in 3D space, x, y, and z, how fast it's going in each of those directions. Now, the microstate is 6 numbers long. The energy associated with that state is a sum of 1/2 mv x squared v y squared and v z squared. And if I choose the same discretization for all three directions, then I can write down Q as 1 over delta x cubed, 1 over delta v cubed, an integral over x, an integral over y, an integral over z, an integral over vx, vy, and vz, e to the minus beta m by 2 vx squared, vy squared, vz squared. Whew. It's quite a number of integrals. But note their structure. Again, we have an energy which is a sum of independent variables. So this is a product of e to the minus beta mvx squared over 2 times m over 2 vy squared times vz squared. So that factorizes again. So I can associate each one of those factors with its own integral. The integrals over x, y, and z are all independent to do. So this whole three-dimensional partition function factorizes, telling me that each dimension is statistically independent. So I'll have a partition function for the x, y, and z microstates, parts of the microstates, and the vx, vy, and vz ways the system can exist. So this says not only are the directions, the x, y, and z directions, independent of each other, but the positions and the velocities are statistically independent. That, I think, is a very unintuitive result. Newtonian mechanics tells you that if I know the position and the velocity, I can predict the trajectory of a particle for all times. Here, the simplification of thermal equilibrium is such that if I look at a particle, if I make a measurement of a particle and note its position, and simultaneously note its velocity, if I make continued measurements of that system, fluctuations in the position of the particle, where it goes, are statistically uncorrelated, statistically independent of how fast it's going there. If I go through and do all these integrals, I'll have 3 factors of L. That gives me a volume in units of delta x cubed. I'll have 3 factors of this 2 pi beta m square root of, which gives me that to the 3/2, and that's all in units of delta v cubed. If we take, again, delta x, delta v to be h over m, this whole factor here must have units of length. Cubed. Oops. So let's define that as a length. Let's define it as lambda cubed, which means that our whole partition function is a volume in units of some temperature-dependent length cubed, where that length is 2 pi m over beta h squared square root of. Now that also should look a little familiar to you all. That is what old de Broglie called his thermal wavelength. So what we've just learned is by using the resolution implied by quantum mechanics, essentially the number of ways a particle can exist in a three-dimensional box is just the volume of that box in some cell size that's given by the thermal wavelength. And that fact that that length is temperature dependent, that it really means that there's an effective length, an effective size over which I can grid up space that depends on how fast the particles are going, what that temperature is. That's a little unclear. Let me try that again. Smeared out by T. Okay, we can even go a step further. We could go to n particles in a box with volume V. The energy for n non-interacting particles is just all, if they all have the same mass, is just their kinetic energy, which is m over 2 summing over all the particles, vector v squared of each of those particles. Do a better v, which is just the kinetic energy of particle 1 plus the kinetic energy of particle 2, all the way up to the kinetic energy of particle n. And now it's the same old game. That energy is a sum of independent variables. The energy is a sum of particle variables. I could write it as the kinetic energy of particle 1 plus that of particle 2, which means that we'll have a factorization again. I really am just a one-trick pony. This is all I got. Q will factorize again, and so now we'll have Q is some single particle partition function raised to the n, where that Q is what we've already computed, just V over lambda cubed. With one little catch, if the particles are all the same, I've overcounted by a permutation symmetry. Okay, well, that's all well and good. We've essentially solved all systems of particles that just have kinetic energy. We have it now for arbitrary number of particles, for arbitrary dimensionality. If you really wanted to, you can ask for how do n particles fluctuate in a d-dimensional box. What can we say about non-ideal systems? What about if the gas actually interacts? Well, then the energy of the system would be the kinetic energy, which would depend on the velocities of particle 1, particle 2, all the way to particle n. But in addition to the kinetic energy, if they interact, there is some potential energy that will depend on their positions. But notice the structure. The energy is a sum of something that depends on positions, potential energy, and something that depends on the velocities, the kinetic energy. So if I wrote down Q, well, there's going to be a piece. Let's do things in units of h over m, as implied by quantum mechanics. I have a bunch of integrals over velocities. And I could put that kinetic energy factor there and separate out completely all those integrals over position with the associated Boltzmann factor from that potential energy operator, not operator, potential energy function. This, I can call Q configurational. That's probably really hard to evaluate. I need to know that function of the potential energy and how it changes with particle arrangements. It's not going to be simple because I'm going to need to know where particles are relative to each other. So it's not a function of just individual particle labels, but pairs of labels at a minimum. But this is something that we've already just evaluated. We evaluated it just a second ago. It's just going to yield 3 n factors of that thermal wavelength. So this, hard to evaluate. But nevertheless, the whole partition function is just whatever that configurational bit is divided by 3 n factors of the thermal wavelength. So independent of how particles interact, the statistical independence of positions and velocities means that we can always integrate out the velocity fluctuations. And thus always there will be an average energy, which is given by the derivative of log Q with respect to minus beta, which through this product form will be a configurational part plus a kinetic energy part. That kinetic energy part is something we have evaluated and know how to evaluate. In this case, will be 3 n factors of 1/2 kBt. This is some average potential. And so the average energy is always decomposable into a piece we know how to evaluate. This is always true for a classical system. And then some piece that's probably hard, the potential energy piece. Nevertheless, if I restrict myself to a discussion of just the kinetic energy, it's always 1/2 kBt per v squared. So if I have n particles in 3 dimensions, I'll get 3 n factors of 1/2 kBt. In one particle, in one dimension, I have just 1/2 kBt. So the average kinetic energy of a liquid, which interacts quite strongly with its neighbors at 298 Kelvin, is identical to the average kinetic energy of a gas at 298 Kelvin. Independent of what that gas and liquid are made up of, how strongly the liquid interacts with itself, or how weakly the gas interacts with itself, if I set the temperature, I have set the kinetic energy. So in fact, this gives us probably the most robust means of microscopically identifying the temperature as just the kinetic energy of the system. Mind you, one that is classical. All of this is predicated on being able to separate out the statistical independence of x and Vx, which quantum mechanically is not allowed. Yet, at least in the high temperature limit for macroscopic boxes, that's not a bad approximation. Classical mechanics works pretty well. In the next couple lectures, we'll find that this relationship, 1/2 kBt, these factors of 1/2 kBt, there's a slightly more general way to state when you should expect average energies to take that form. And so that's something we'll explore soon. All right, well, that's all I have to say. So hope you all have a good weekend. One quick announcement, I'll make this in the live session on Thursday as well. Your midterm is coming right up. It's next week. So a week from this Thursday, which is the 1st of October. The protocol for the exam will be as follows. I will post an exam sometime on Thursday. I'll send an announcement for when to expect that posting. You'll have 24 hours to take the exam. I've written it such that it should only take about 2. You are free to use any of the course provided materials. So, open book with respect to the notes and with respect to the problem sets, their solutions, the discussion sections. I would ask that you work it yourselves. So this should be done independently. While I hope that you are working together for the problem sets, the exam should be done by yourself. I would also recommend that you not look at the internet for answers. Statistical mechanics is not the easiest topic, and more likely than not, solutions you might find on the internet are probably wrong. And I've written questions with that in mind. I think you'll have fun with the exam. I think it's a fun exam to work through. So if you have any questions, bring them to the live session. We can discuss the practicalities of this as well. All right, everyone be well.